Fundamental axioms that any explanation method has to follow. No exceptions. If you're going to claim you can look inside the black box, you have to play by these two rules. So rule number one is sensitivity. Basically, it says that if you change something in the input, like say you Photoshop the lens off that camera, and the AI's prediction changes because of it, then that lens has to get some of the credit. Simple, right? If it makes a difference, it counts. Then you've got rule number two, implementation invariance. Now this one's a little trickier, but stick with me. Imagine you have two AIs. On the inside, their code is totally different. But on the outside, they behave exactly the same. You give them an input, they give you the exact same output. Every single time. Well, this rule says their explanations have to be identical too. The why should depend on what the AI does, not on how its code is wired up. So, the AI looks at this picture and it correctly says, yep, that's a fireboat. Awesome. But then when we use that simple gradient method to ask why, look what it highlights. It's pointing at the water being sprayed and the bridge in the background. The actual boat barely gets a mention. So what's going on here? Well, the AI is already so sure it's a fireboat that changing a few pixels on the boat itself doesn't really change its confidence much. Its score kind of flattens out. And because of that, the gradients for the boat are almost zero. This is a total violation of rule number one, sensitivity. The most important feature is getting ignored. So let's just recap where we are. The simple gradient methods, they totally failed the sensitivity rule. They can get, well, saturated and just completely miss the point. Now, people knew this was a problem, so they came up with other, fancier methods. You might have heard of LRP or deep lift. They fixed the sensitivity problem, but guess what? They broke our other rule, implementation invariance. Their explanations would change based on the internal code, even if two networks were functionally identical. So we were stuck. Okay, so every method so far has failed our two-rule test. It feels like we've hit a brick wall. But this is where the hero of our story comes in, integrated gradients. So how on earth does this thing work? It's actually a beautiful, elegant idea. Instead of just looking at the final image in isolation, here's what you do. You start with something totally neutral, a baseline. Think of a completely black image, just nothingness. Then you imagine a straight line, a path, from that black image to your final picture, and you walk along that path, taking hundreds of tiny little steps. At every single step along the way, you stop and ask the AI, okay, from this point, what's important? You calculate the gradients at that moment. And at the very end, you just add up all the answers you got from the entire journey. You integrate them. It's like collecting clues along a path instead of just looking at the destination. And that is the magic trick. Because you're adding up the clues from the whole journey, you never get that saturation problem. So boom, it satisfies the sensitivity rule. And because the whole thing is built on the pure fundamental math of gradients, it also satisfies implementation invariance. An AI was trained to spot signs of diabetic retinopathy. That's a disease that can literally make people go blind. So on the left, you see the scan of the patient's retina. On the right, integrated gradients shows us the exact spots, those tiny lesions that the AI used to make its diagnosis. This is a game changer. A doctor doesn't just get a yes or no from a black box anymore. They get to see the evidence. They can verify the AI's reasoning. That's how you build real trust. And this isn't just for pictures. You can use the exact same idea for language. Here, an AI is trying to figure out what kind of answer a question needs. And integrated gradients lights up the trigger words. You can see it correctly figures out that how many is looking for a number. But here's the cool part. It also helps you debug. Look at this. For some weird reason, the model thinks the name Charles is a clue for a yes-no question. That's a bizarre hidden bug you would never have found without being able to peek inside. I mean, the range of this thing is just wild. We can even take it to chemistry, using it to predict a molecule's properties. The method highlights which specific atoms and bonds are the most important for that molecule to do its job. And this goes beyond just checking the AI's work. This is about discovery. The AI can point out things that scientists might have missed, literally accelerating scientific research.